And so, are both these on? This one, other one, right. And so, right, similar to how we have current always flowing along the path of least resistance, we'll have the magnetic field flowing through this ferromagnetic material. And so, right, what we can do is we can generate higher currents with fewer turns, turns of the coil. So how does a ferromagnetic material respond to AC current? And this is figure 2.2a from the text. It does a very good job of describing something we call the hysteresis loop. Okay, so it's how many of you guys have seen this before, the hysteresis loop? Okay, so what it does is it describes the relationship between the flux density and the magnetizing force for a ferromagnetic material, and it doesn't have a directly linear relationship as one would expect. All right, so right, y-axis will be, so this is RB, okay, magnetic field intensity. Our x-axis will be the magnetizing force. And sorry, I didn't label these right, or I didn't state right. So this is flux density here. And H, as we've seen before, is the magnetic field intensity. Okay. And so ferromagnetic material is subject to saturation. So what we'll see here is that with regard to flux density, we will have saturation values. So up here, this is the saturation of the ferromagnetic material. And we have a corresponding saturation on the negative end. So I'll call this minus saturation. And so if we pick a starting point, for example, right, the hysteresis loop represents essentially a flow of, let's say we start from right here and we increase the magnetic field intensity, what happens to the flux density? So if we start here, I got to draw this properly. Okay, so So this is what the hysteresis loop looks like. So when we get to a saturation point and we quote-unquote turn around, okay, let's say we increase our magnetic field intensity to the point where we have saturation, and then we pull that magnetic field intensity back. So when we pull that magnetic field intensity back, what we'll see is that the relationship between B and H is different, right? So we move, increase, 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 we get to saturation, we come back, and we have a different path. And the hysteresis loop, right? You don't have to go all the way to saturation in order to encounter hysteresis. Anytime you essentially have a positive flux density and you come back to where you were, you'll have that same behavior. So you can draw little mini hysteresis loops in here. Right, you can see there's smaller ones that would be in there. Okay, and so when we increase the maximum or the peak of the magnetic field, I think I spelled that wrong, but I'm going to leave it. We increase the width of the hysteresis loop, which you can see from the picture. Okay, now, another figure shows us the, so we can ask the question, so how does this behavior relate to permittivity? Okay, so I'll draw a mini version of the graph we have above. This is figure 2.22b from the text. Again, with the y-axis being the flux density and the x-axis being the magnetic field intensity. Okay, and so here, if we have part of the hysteresis loop, which looks like this, and then it would go back and do that, but we're not drawing the full thing. So this section of it here, okay, the slope is, it describes the permittivity of the ferromagnetic material when not in saturation. Okay, so this is what we could refer to as sort of the linear region of operation. And then up here, the slope is dependent on two different things. It's going to still be dependent on the permittivity of the ferromagnetic material, but when it's in saturation. When it's in saturation, it's going to get increasingly high, right? Just how the gain of an amplifier when we go to saturation gets increasingly low and goes to zero. Same thing here. So it's dependent on the permittivity of the ferromagnetic material, but also the permittivity of air. So here, this is also dependent on the permittivity of air. But, again, because we have a lower resistance path in their ferromagnetic material, the permittivity of air is not going to have much of an effect. The flux lines are not going to be taking that path. The opposite occurs up top. Now the ferromagnetic material has become very saturated, and so the slope here is predominantly dependent on the permittivity of air. For both the triangles, it's actually dependent on both, but one is negligible. In the bottom, the permittivity of air is negligible, and at the top, the permittivity of the saturated ferromagnetic material is negligible. And so we can call this the linear region of operation. And we'll call this saturation. So to just give some sort of detail there. And so saturation occurs, like I said, when we have the magnetic field and the flux lines predominantly flowing through the air as opposed to through the ferromagnetic material. Okay, now, next question is, what is the I can't talk today, magnetomotive force?
Professor,
Mm-hmm.
is it sort of like how with like resistors, the resistance sort of changes how much current goes through because of heat?
Yes and no. I'm not that much of an expert on the electromagnetics and to comment that well. And I'm the person I don't want to give answers that are not complete. So I could probably piece together an answer, but I don't think it's better if we either take a closer look at that at another point, or yeah, I'm going to just defer that question. I'm sure that heat plays into it. Let's put it that way.
Well, and also that like heat, but sort of like that it's. Well, I think saturation is a very fitting term where it's sort of like this is like the H field that it can handle, or like this is the max. Sort of like it can only handle so much B field, and then it starts going through like leaking through other places. Is that sort of what happens?
Mm-hmm. Yeah, most definitely.
All right.
Yeah. In a similar vein to how we have charge carriers when we talk about current flowing, right? Within the ferromagnetic material, within the material itself, there's a certain amount of magnetically charged particles that are, anyway. So, again, my very poorly put together explanation. Once we have used up all of those magnetically directed or charged particles, we'd be in saturation anyway. That's not a very good explanation. Okay. So continuing on, magnetomotive force, which is when we talk about, there's a lot of parallels between electric circuits and magnetic circuits, right? So we have electromotive force, EMF, which is what we call a voltage source, another term for a voltage source in electric circuits. So magnetomotive force is going to be the equivalent to that in the magnetic circuit, which is essentially the force which causes the magnetic field to flow. So the magnetomotive force, equation 260 from the text, tells us that the magnetomotive force is equal to the flux times the reluctance which is this fancy looking R. So this is reluctance. This is our flux. And this is our MMF, magnetomotive.
Is that a mu or an M?
It's an M. M, yeah. And so this reluctance value will increase drastically for saturation. So that is similar to what we see in the hysteresis loop, is that right, the reluctance, which is equivalent, quote unquote, to resistance for the magnetic field, and so you can see sort of a V equals IR type of relationship being set up, right? Where the MMF would be the voltage, the reluctance would be the resistance, and the flux would represent the current, which is the amount of magnetic energy that's flowing through the circuit. Now, next question, which is skipping around a little bit, but we have to hit a couple of important topics. We still haven't discussed how do we define mu m. And we want to do that relative to mu naught. Mu m is, I didn't label it, right? That's mu m right here. And then up here, okay. So what we're going to use is a relative value. Equation 257b from the text says that the permittivity for the ferromagnetic material can be defined as using a relative value times the permittivity of air. And this is more of an equation that you have to just know in order to do the textbook problems. Not that it's not important, but I mean, in another textbook, they could just choose to give you the permittivity of the ferromagnetic material directly. So this is the way that they do it here. Okay, and one interesting thing is that this can be much, much greater than mu naught. Although, maybe that should not be that surprising, right? The permittivity of air is not necessarily that high, and we know that metals, right, can be very, very conductive to electricity, and they can be also very, very conductive to magnetic fields. Yeah?
What is mu r?
Mu r is this relative value. So what happens is, for a problem, they may give you the permittivity of air, and then instead of giving you mu m, which is the actual permittivity of the ferromagnetic material, they'll say the relative permittivity is whatever. And so you have to know to multiply the two together in order to come up with the ferromagnetic, or the permittivity of the ferromagnetic material. Again, that's why I'm saying this is not necessarily something I think that's, so hard. I mean, whatever. It's just for the purposes of doing the problems, right? If they give you these two, you have to know to calculate the third, or you won't be able to.
Usually give that on the data sheet, right? Of
I guess. I mean, I'll be honest with you. I don't read that many chord. I'm not trying to be like sarcastic. Yeah. I mean, I assume there's a reason why they're presenting it this way. That this is
I
the
see
problem.
it that way so that they can say your relative permittivity is 3.2 rather than making this big long number that you have to.
That makes sense. It's also an easier way to describe it, right? As opposed to.
This is like X amount of times air rather than like
Yeah.
putting a number. They can sort of be like harder to find without looking at what mu naught is.
Makes sense.
Yeah.
Definitely is easier than saying 2.65 times 10 to the whatever. Okay, so moving on. Okay, section 2.8.4. Is flux. Within power systems, it's actually funny. You have, I mean, we only, for better or for worse, have one course that we can devote to it. But I mean, I did my graduate work on power systems, period. And within a course like this, there's component level stuff, system level stuff. And for example, when I did my graduate work, there was almost no component level work that went into it. I was not worried about transformer modeling or machine modeling. There were a lot of people who worked on that for their graduate studies. But mine was all actually the stuff we're going to get to at the end of this class, which is system level analysis, which I personally think is more interesting, but some people might disagree. And that has to do with load flow analysis, economic dispatch, essentially the nonlinear analyses and the mathematics that go along with it. Go along with solving those systems. So this is very interesting information. It's not necessarily what I spent a majority of my time studying, like ferromagnetic materials and that type of stuff. But it is important, obviously, to understand material later on. All right, so now let's talk about flux. So this is another figure from the book. 2.23, and it shows the beginnings of how we are going to describe a synchronous machine. So let's say we have this cross section here, poorly drawn, and we have coiled wire mounted to it. And so what you can see is that where there's an X, that represents the coil flowing into the board, and where it's an open circle, it's out. So you can imagine it's sort of like the coil's going like that, and then it's wrapping around the ferromagnetic material as shown here. So we cut it along the axis where the turn of the coil is not shown. All right. Now, like we've been talking about so far, right? We have this wire wrapped around our ferromagnetic material, which is what is the middle of the red. And if we have an electric current flow through those wires, then what we'll see is the flow of magnetic flux. Right? Flux will flow in response to a magnetomotive force, which is affected by the current flowing through those coils. And Now, what we can do is take a look at the cross-sectional area of the core. And the area of this cross-section we're going to call AM. Okay, so now we can use equation 260 to give us a different representation of this magnetic flux. So we have phi m is equal to the cross-sectional area of the core times the permittivity of the core, the ferromagnetic material, times the number of coils, turns, times the current flowing through, divided by, remember that's the mean path length. This is also equal to another version, or just I don't want to say recalculation, but shifting of the elements. We can also call this is equal to N times I divided by the reluctance, where the reluctance is then equal to the mean length over the permittivity of the ferromagnetic material times the cross-sectional area. And so if you compare those together, right, they all end up giving us, should all coincide with the same value, right? Because if we put this in the denominator here, then anything in the denominator of the denominator will be flipped up top, hence mu m and am, and then the mean path length will stay in the denominator, so it all works out. The unit of flux is the Weber. And so what we see is for reluctance, the cross-sectional area as well as the permittivity play an important role, as you would expect. As the permittivity gets higher, the reluctance gets lower, right? Because those permittivities is a positive value when it comes to, or is proportional to the amount of flux that can flow. Reluctance is inhibitive. And then obviously as the cross-sectional area gets greater, also that increases the amount of quote-unquote room we have for the magnetic field, the flux to flow within the core. Okay, so, right, reluctance is analogous. I've said this several times already. I don't think I have to write it on the screen again. Reluctance is analogous to resistance when we talk about magnetic circuits. It's inversely proportional. Anyway, I've said all this. And one important thing to state here is that these equations So we're going to assume equal distribution of the flux lines within the cross-sectional area. That's stated in several of the problems. And if we don't make that assumption, then the mathematics become a little bit more difficult, and we have to use calculus in order to determine what the reluctance value would be, or what the relationship between the the flux and the magnetic field intensity would be, right? Because it's not uniform. We can't consider it as one chunk. We're not going to deal with that, though. Our goal, predominantly, is to introduce this theory and move on to more large-scale applications of it, okay? As opposed to going down the rabbit hole and looking at more and more complex problems involving flux, flux density, etc. We're going to try to move away and look at, okay, how is this part of transformer modeling? How is this part of synchronous machine modeling? Which, as you know, whenever you're trying to model a system, normally the number of assumptions that you use gets greater as opposed to fewer. Okay. So now, flux linkage. If we assume that all the coils are linked by the same flux, then the flux linkage is defined below. And I'll explain what that means. So why would there be a case where all of the coils were not linked by the same flux? Yes?
You had one coil in between two other coils.
Yeah. So when they're evenly spaced, and we assume that the flux is flowing uniformly throughout the core, right? It's a lot like how we deal with the mutual inductances for the transmission lines. We assume, right, that the effect, because we have a symmetrical design, the effect of one on all the others is the same as their collective effect. You know what I'm saying? Like, you rotating it and looking at any individual coil, it's almost indistinguishable which one you're looking at, right? You look at the first coil, what does the rest of the system look like? You rotate it, look at this coil, what does the rest of the system? It always looks the same. And so that's a sort of intuitive way of understanding, okay, the effect of the coils are equal, right? The linkage is equal. Now, if we had unevenly spaced coils, right, or we had, I think what you were trying to say, we stuck one random coil in there between two others, like it's 1, 2, 3, 4, 5, 6, and we stuck a seventh one randomly in there, then, right, that coil would experience a different flux relationship, or the flux flowing through that coil would be different than the others, potentially. And that, again, would make the math more difficult. So we're assuming that they are all linked by the same flux. Yes?
So that means that they're all getting the same current, right?
Yeah, that's one way of looking at it using the electric circuit analogy. That the current flowing through all of those coils is the same. Okay? Right, so our lambda is equal to the flux times the number of coils, again assuming that the coils are linked by the same flux. So flux flux linkage is an important value, right? Because it does describe the relationship between the electric field and the magnetic field, electric current and magnetic field intensities. Okay. Okay, inductance. Actually, there's a picture I do want to include, sort of something I drew last time. So if you look here, and just imagine that this is a set of coils, right? Then the green flux lines so that will be sort of a visual description of what's going on, right? If we have flux lines that are leaking into the air and it's not equal, I mean, we don't have the same number of leakage lines per chunk along the way here, then our assumption wouldn't hold. Now, obviously, this is a little bit of a different drawing because it's not wrapped around a core, so the circular shape of the core helps with that because the flux moves in one continual path. Okay. So inductance. Inductance is normally the value that we're going to be concerned with in this class when it comes to representing the relationship between the magnetic field or magnetism and magnetic and electric fields. So, neglecting saturation, so this expression specifically is relating a value of mutual flux linkage, right, between two sets of coils and defining it in terms of mutual inductance. We said that this expression holds neglecting saturation, and the reason for that is because in the saturation region there is no single inductance value that would represent this this relationship here, right? We would need a function, a varying function to describe the inductance value. So we're going to neglect saturation and assume that we're operating only in the linear region. And so if we combine this expression with with 260, then what we end up with is this here. So the inductance is equal to, after two different steps and combining some things together, I would go through and show the exact combinations, but there's really not that many expressions we use in this chapter, so I think it's kind of easy to pull out which we're using. Yep?
Is the mutual inductance the variable saturation region, or is that I? The 22 mutual inductance?
It's not, I see the confusion. No, the word variable is correct, but it might be better to say the word variable, I think, was, I don't know if that addressed your question, but for me looking at it, it was a confusing way to word it. Okay, the variable, this equation is for the non-saturation region. The Lm value does not have a single definition in the saturation region. It's variable, meaning that it's changing and not constant. So what was your question?
What's I?
I is the current.
Okay.
Yeah. So anyway, we make those substitutions, and we end up with this definition for the mutual inductance. All right. So now let's take a look at an example. So let's consider a rectangular toroid. Which looks like this. And it has,
Rectangular.
say what?
I'm not sure what a toroid is, like geometrically.
This is the picture.
Alright.
That's what I was just about to make a joke about how I never know what these words mean until there's a picture drawn because they're used so infrequently. A toroid, a rectangular toroid, again, I'm not a geometry person, is essentially just a cylinder with the inside cut out. So rectangular mean that, like, if you look at the side view of it, it looks like a rectangle. And then toroid meaning it's a circle with the middle cut out.
Toroid just means something that has a hole in
Yeah, exactly.
The donut shape.
Donut shape, yeah.
it, but not necessarily like
It doesn't necessarily have to be only, I guess if you say toroid by itself, it does imply donut shape, right?
I I
Does
think
it?
there can be, like, sort of things that are not round, that have a single hole in it. And then, like, a Toroid would have two holes in it. A double donut.
Sounds good to me. I want breakfast now. Let's shut down class, get some donuts. Anyway, to make a long story short, this is what it looks like. All right, and for your quizzes or exams, I'll give you the shape. I'm not going to be expecting anybody to know what a double donut versus a triple donut
My
is.
mom
Okay.
was a topologist.
Yeah, oh, she's in yes. I was going to say you're right. She would know. Yes, yes, yes. I've read who I was talking to. Don't tell her I don't know what a toroid is.
Don't tell her I'm unsure.
No, wait. Roll back the video. Toroid is very important. Okay, so we got some wire wrapped here. Okay, the cross section has a radius r. It has a height or length, depending on what well, I guess we're going to call it height.
Is that the outer or the inner radius?
This is the outer radius. Yeah, so it goes all the way from there. And then, lastly, we have a width, or we could call it inner width. And hopefully you can see where the arrows are pointing. Right, that's the thickness of the delicious part of the donut. All right, so it asks us to calculate the coil inductance assuming linear operation. And what do we know? So the width is 5 millimeters. The height is 15 millimeters. The mean path length is 18 centimeters. The relative permittivity is 5,000. So 5,000 times more permittive than air, and the number of turns is equal to 100, not 1,000. Okay, so what we're going to see here is that more so than this being a conceptual problem where you're really going to be looking at the operation of the coil and the magnetic fields and drawing lines, it's going to be more about just combining together the equations that we've already stated. So that's sort of the level at which we're going to be considering these systems. You have a set of expressions, and you're going to be given knowns, and just combine them together to get the unknowns. So we're going to use 264 to calculate our reluctance.
You know what radius?
Look at the book. Look at the book. Well, that's millimeters, definitely. That I remember saying. I just wrote through. Really small, really long. My pencil. Can you grab it? It went sort of like diagonal. There you go.
Here you go.
These are the parts where I hope if someone ever watches this video is like, what the heck is going on? Yeah, these are the Easter eggs that you only get if you watch it all the way through. All right. So no. Although I guess by them giving us the mean path length, that would imply what the radius would be, right? Because the mean path length would be the length that it has to travel around the center here.
Yeah, I'm just trying to like figure out what the cross-sectional area would be.
Yeah, yeah. Okay. So, use 264 to calculate the reluctance. And so these values, how many of them do we know? We know that this is 18 centimeters. We know that this will be essentially, right, so the cross-sectional area is, looking at it from the point of view of current flowing like this, so it's actually a rectangle, right, the cross-sectional area. So the cross-sectional area is width times height. Which is 5 times 10 to the negative 3 times 15 times 10 to the negative 3. Which gives us 75 times 10 to the negative 6 meters. Okay, and then the permittivity, right, mu m is going to be equal to the relative permittivity times the permittivity of air, which then is 5,000 times 4 pi times 10 to the negative 7 henries per meter. Okay, yes?
How come we're using W when calculating the area? Because shouldn't it's going to be
No,
W times 2R. It's 2R tall, correct?
No, this is right. It's W tall, because if you think about it, if you're traveling inside of this, you're one of the magnetic flux lines, right? What do you see? You see a cross section that looks like this, right? So from your point of view, it's a window that's W high and H long.
Basically, you want to cut it and roll it out as if it was a rectangle.
Yeah, so let's say I slice this right down the center, right? What I would see is I would see one rectangle, and then I would see another rectangle at the bottom, right? I would see two cross-sectional areas. So one of those cross-sectional areas would be W times H. Okay, and so when we combine those values together, and so here it's important to keep your units straight. So we have 18 times 10 to the negative 2 meters over 75 times 10 to the negative 6 meters times 5,000 times 4 pi times 10 to the negative 7 henries per meter. It always helps in stuff like this to keep track of units. So that will go away with that, and what we'll be left with is when we multiply everything out. Yeah.
Wouldn't it be meters squared for the area?
Ah, yes.
Yeah, so you should end up with just 1 over,
Yeah.
and then,
So that means there's a meter squared there. So, okay, so we end up with 38.2 times 10 to the 4 meters over, no, just, so then this goes away with this. And so we're left with 1 over henries. But, okay, so this is the same as if you go to the core SI units, because in order to get the units to work out correctly, which should be amps per Weber, you actually have to go all the way back to like the core values, which is like seconds, meters, kilograms. So this is equal to 1 over kilogram times meter squared, seconds to the negative 2, amps to the negative 2. So that's if you just take the definition of a Henry and go percolate it all the way back to keep going back, substituting to the core.
Would you find that the inductance isn't Henry and you didn't have inductance, like the question is asking for?
But we're not at that point yet. We're finding reluctance right now.
Yeah, but I mean, like, 'cause, like,
It'll all substitute out. I see what you're saying, but I do want to have everything at least intermediately in the proper units. This is not necessarily something you're going to have to do for a homework or a quiz problem, but in the examples, I want everything to have proper units. So if we go and we take that intermediate step, what we see that this is equal to amps per Weber. Okay, which then gives us the reluctance in the value that we are that we're expecting.
So it's the same 38.2 times 10 to the 4 amps per Weber.
Yeah. Okay, step 2. And we are almost done. That's it. Was just calculate inductance from reluctance. That's it. And inductance is equal to a unitless value, which is n squared, over the reluctance, which is then going to give us 100 squared over our 38.2 times 10 to the 4. And we'll just go ahead here and use 1 over henries to make things easier. And we end up with 26.18 millihenries. All right, and so that's a good stopping point. Next time, you will have the quiz, okay?